All right, so we want to finish up the discussion of Fraunhofer diffraction and start the Fresnel diffraction today. This is just a quick reminder of what we discussed last class, that diffraction limited resolution in imaging is governed by the 80 disk pattern that we derived or that we talked about for circular apertures in Fraunhofer diffraction. And so, for example, if the angle between two sources is delta phi, then the minimum angle that can be for the resolution, that is the minimum angle between these 2 points, is equal to delta theta, where delta theta is 1.22 lambda over d. This is the Rayleigh criterion for the minimum resolvable angular separation of two objects, such that they can be imaged in a lens, with a lens, or actually also true for telescopes and things like that. And the minimum then distance in the image plane, delta L, is of course just F times that angular separation. And this is shown here, for example, at the limit of the resolution. And then in the last class, as I was explaining, that if you sketch the intensity, this is roughly what it would look like. You can see a little dip in between the two peaks. That corresponds to the minimum resolvable angular separation according to the Rayleigh criterion. Okay. So I just want to do a quick example. I mean, we did one example sort of in the last class where we discussed the when you're looking at the TV which has LED pixels, then what's the minimum distance at which they become no longer resolvable and you can't see the pixels in the LED display. This is a very similar problem, but now with a telescope. So we have a primary mirror diameter for the Mauna, for the Keck optical telescope, and that is 10 meters with a focal length of 117.5 meters. The diameter of a sun is given by that number, and we're going to take the wavelength of light at which this is happening, where the imaging is being done, as 500 nanometers. And we're asked at what maximum distance L from the telescope will the Keck optical telescope resolve to sun-like stars? So meaning the stars have roughly a diameter of the sun. Okay, and we are going to assume everything else is perfect. So effects of atmospheric turbulence and all that has been canceled out. So the only limitation on the image resolution is the diffraction limit that we just discussed, the angular resolution from diffraction. So there. So, okay, so the basic idea of this is fairly straightforward. It's just using this angular separation that I just talked about. So we model the mirror as a lens as well. And so we have two stars over here at a distance capital L from the telescope. And they are going to result in an image. Sorry, that wasn't a straight line. Okay. And then similarly, this is going to result in an image over here. And so we can calculate this angular separation delta phi, and that's going to result in a resolvable image over here. So, so we have that delta phi, of course, minimum that is resolvable in this telescope is simply 1.22 lambda over d. Okay. And both of these will give rise to a airy disk pattern here, and that's what sets this minimum resolvable separation. And now, since we are imagining effectively that these are in the same plane away from the telescope, we can now find what is the minimum separation. Let's call this delta y in the object plane. Well, that must be equal to L times the minimum delta phi, right? And what I'm going to do is I'm going to set this to be equal delta y to the diameter of the sun. Because we have said that these are sun-like stars, so we can set that diameter or the separation between them, and that's exactly equal to a diameter of the sun. That's when these two will be resolved. So basically equating all of this, we have 1.22 L times lambda over d, where d is the telescope mirror must be equal to d of the sun. Okay, and that is then you can now find what L will be from this expression. Okay, so I'm going to just stop. I'm not going to put the numbers in. You can do that yourself. Any questions on that? This is similar to the pixels in the LED display problem. That's slightly different because now we're asking for the distance between the stars instead. Okay, so that brings me to another important sort of result, something that is not in your textbook, but I thought is something, such a cool thing that you should know about this. The Heisenberg microscope. How many of you have heard of this expression, the Heisenberg microscope? No one. Oh, interesting. Nice. So the origin of this story comes from Heisenberg's failure during his PhD defense. You all know who Heisenberg at least is. You've heard the name Heisenberg. If not in this, then in Breaking Bad, presumably, if you watch Breaking Bad. But if you're a physics student, hopefully you've heard the name Heisenberg at least before. So he failed his PhD defense, by the way. The reason was that he was a terrible experimentalist. And he had no idea that a microscope had certain limitations. And the limitations, which we have just read about and we have understood better than Heisenberg did at the time of his PhD defense, is given by the wavelength and the psi and the d. By the way, I omitted this, but if you look right, it's the separation was lambda f over d. Well, you may remember that there's something called an f number from way back in geometrical optics. F number is defined as f over d. So this is basically exactly the same as lambda times the f number as well. Okay. All right. So anyway, so he didn't know this, and so he failed his PhD defense, had to go back and relearn this topic. And while he was doing that, he came up with this interesting thought experiment. And the thought experiment was, if I take gamma rays and I put them onto an electron, which I'm trying to image with a gamma ray microscope, basically, and he knew you had to use something very short wavelength because the electron position is presumably very small. So he began to see, okay, what is the minimum position that I can resolve the position of the electron with, okay? And we have just read that this is indeed proportional to lambda over d, and then f as well in the numerator, but that can be rewritten as lambda over sine theta, where theta is the maximum angle subtended by the lens, this lens over here at the particle. Okay, it's just, all this is just equivalent ways of writing the same thing, yeah, especially for small angles, which, anyway, so, which is all he was trying to get to, an order of magnitude. Well, it also turns out because of the particle nature of waves, right, which the photoelectric effect had shown, that gamma rays have a momentum which can be written as h over lambda, and then it turns out that the maximum uncertainty in the position because of the scattering of these gamma rays on the electron is going to impart a momentum to the electron. Okay, so the electron will get a momentum that is uncertain to within this number h over lambda sine theta. I'm not going through the proof here, but you can understand this by going through the steps of momentum conservation, basically, with the electron and gamma ray. And though the product of these two, the electron position and the electron momentum uncertainty is h. Okay, and so this was the big result, the uncertainty principle that Heisenberg showed. I mean, this was the thought experiment that led him to this result. Then, of course, he had to prove this more theoretically and more rigorously with like actual, other methods. But, this was sort of the physics of the uncertainty principle. So just in case you never knew about this, this is now something hopefully that you'll remember. So it came about because he failed to learn optics. Okay. And it's a good thing, right? He waited so long to learn it that he actually understood where to apply it in some problem that he was thinking about at that time. Okay. I don't recommend that, but it's certainly interesting. Okay. All right. Some more applications of this resolution limit, the diffraction limit for resolution. Here are some, beautiful pictures of optical microscopes that are being used to detect things in the cell, in a living cell. Also with electron microscopes, we now can like also similarly, there's a limit to the way in which electron microscopes can like image structures. This is for some insect that the electron microscope is imaging those things. But also, for example, in art, so Seurat, one of the famous French masters in the painting, he was what they were doing. He and other people invented this type of art called pointillism, which you might have heard of, where what they did was they took little dabs of colors of like small little points, and so instead of like trying to blend the colors with like brush strokes, at each point they put like one of these dots of different colors. Okay, and the dots were chosen carefully such that when you stood at a normal viewing distance from a portrait or a picture, all the colors blended into one because your eye could not resolve those tiny little dots. So this was pointillism. So this is the same idea has been used in like many different things, technology, art, etc. Okay, so all right, so that's what I have to say about the Fraunhofer diffraction. Any questions on the resolution limit, the diffraction resolution? I should mention that if you read some more, you'll see that in modern times we have discovered ways to get around this diffraction limit. Okay, you might wonder how is that possible? Well, there are many ways in which you could do this. First of all, of course, the Rayleigh criterion that we used is somewhat arbitrary. Why should it be that the two peaks are only resolvable at half the, or when they are equal to this delta theta, when separated by half a line width, or basically of the that's a sort of arbitrary criterion, and so you could like certainly imagine improving that. And then nowadays with modern digital computers, we can also like digitize the signals coming from the system, and based on signal to noise, we can do some tricks with curve fitting and try to get that thing down further. That's another trick. But then there's also the one most important maybe idea, which is that so far we've been assuming that all of the things that we're measuring are proportional to the intensity of the photons that are arriving at the detector. That is the signals and the everything, remember, was set up by like looking at what is the intensity of the airy disk pattern. But what if we could do something more clever where we weren't just measuring intensity but some nonlinear response to the electric field? It turns out by like choosing some careful patterns of like detectors, or rather actually like some non-standard detectors which have like non-linear responses to the electric field beyond just the intensity. Intensity is E squared, so that's also non-linear, but going beyond that, for example. Then it turns out that you can actually beat this Rayleigh criterion further. Okay, and I don't have time to talk about that, but that actually ended up winning a Nobel Prize in 2014 in chemistry. So it was very again something that people had this diffraction limit for 100 years or something, and then somebody came along and said, well, let's see, can I beat this diffraction limit? And they were able to, under certain circumstances, do it. But under most circumstances, we're dealing with like normal detectors, normal things, it always applies. Okay. Now I'm going to move on to another topic, which is Fresnel diffraction. So I'll quickly remind you the difference between the Fresnel and the Fraunhofer regime. We have said that the distance to where we are observing the diffraction pattern has to be greater than this criterion. This is the b squared over lambda, b being the size of the slit, lambda being the wavelength. And in that condition, you are in the Fraunhofer regime. Another way to think about it more physically than this is that the incoming and outgoing waves that go into the from the object, from the source and then the image plane, those have to be nearly planar. So we can like approximate the incoming and outgoing waves as nearly planar. And that then leads to the fact that the path difference across from like these 2 points from A to B is linear in the aperture variable. That is the aperture variable representing a point in the aperture. So obviously to violate that, then we need that the conditions for the near field or Fresnel diffraction are such that now this distance d is lesser than the area of the slit divided by lambda. Okay, so instead of being, sorry, I should have used r as well there instead of d. Apologies. So this is r. R is lesser than A being just the area of the slit, which is B squared. Okay, same idea. Now we can have either the source wave is no longer planar, has some curvature to it when it hits the slit, or the outgoing wave is no longer planar and it has some spherical wave type behavior as it's going to the image point. So also from like experimental setup, which you've already seen in the labs, if you have collimated beam coming in, and then the slit is placed here, and now if you have a lens which you put such that it images the source point, but not the slit itself onto the image point, right? So the slit itself is effectively at infinity relative to the image plane as well. But instead, if you now take a lens and image the slit itself onto the image plane, which is the screen or whatever you're observing in, now you're imaging the near field of this slit, basically, because you're actually observing the geometrical image of the slit itself, plus whatever diffraction is happening due to the fact that the incoming and outgoing wavefronts are no longer planar. In fact, in most setups, we'll have the incoming wave be planar and just do this to make the outgoing waves not be planar anymore. And that is the Fresnel diffraction setup, which I'm sure you're all now familiar with from your lab. Okay. So one thing that happens is that in the near field or Fresnel regime, it turns out that some of the approximations that we made in the Fraunhofer regime are no longer valid. So one of the things, the problems that we ignored in the Huygens Fresnel principle, remember, is that we said that there were these secondary scatterers when the incoming plane wave hits this aperture. There are secondary scatterers which give rise to outgoing spherical waves. Well, you can also ask, well, if it's truly an emitter of spherical waves, what happened to the backward going waves? We have completely ignored that problem so far. Okay, we've said that that did not matter. So where do those what happens to these backward spherical waves? Are there actually backward waves propagating from the slit? These are questions you can certainly ask. So we introduced something called the obliquity factor. And this is just a function k of theta equals 1/2 times 1 plus cosine theta. I'll sketch it out in a minute. So what it does is basically, if I take the forward going wave like this, and I look at any point P that is, say, over here or here, then there's an angle between that point P and the forward going wave, okay? That angle theta goes in here. You can see when theta is 180 degrees, which would be all the way back here, cosine theta is -1, so this obliquity factor goes to 0, okay? Where's the justification for this? Of course, I can't justify it to you from anything that we have discussed. You have to do a rigorous justification from what I mentioned at the very beginning, which is Kirchhoff diffraction theory. But the physics picture is over here, which is that, again, just sketching out, you have our outgoing wave, you take a secondary scatter or secondary source over here on the wavefront, and then you sketch the outgoing wave vector, k, and then you look at some point P over here, you find the angle theta between them, and then the obliquity factor, if I sketched it, now I've just rotated this so that k is along the x direction and P is along this direction. So I just rotated everything downward. This is the angle theta, then this is what the obliquity factor would look like. Okay. It's k of theta is 1/2 1 plus cosine theta. So on this direction here, the value is 1. Then it decreases down to 0 as you go by 180 degrees. And obviously it's symmetric whether you go that way or this way. Okay, that's just the factor. I can't justify it as I've said. But by using this, Fresnel, who came up with this theory, was able to derive some really interesting and beautiful results, especially when it came to things like, as you'll see in a minute, like the diffraction pattern from like spherical apertures and so on. Okay. So the idea that Fresnel had was we have an outgoing wavefront. Here's a source. Okay, this is the primary outgoing wavefront. From each of these sources in the primary wavefront, we have to construct now secondary wavefronts according to Huygens Fresnel's theory. Now, this is a very difficult integral to do directly or rigorously. Okay, as I said, it took a while before we got rigorous results from, say, Kirchhoff and so on. But what Fresnel argued is that there's a different way to measure what happens from these secondary wavefronts. What he instead did was he drew a sphere from the point P, the observation point, and first he chose a radius R0. Okay, So R naught is the distance from the point P to this primary wavefront. And of course, the distance from the source to the primary wavefront is rho over here. Okay. So the distance between S, the source point and the image point is rho plus R naught. And we also see a point O prime, which is basically diametrically opposite to the point O on the primary wavefront. Okay. So what are we doing here? Well, we're now going to construct a spherical, it's not shown here, but imagine a sphere that is centered around the point P with a distance R naught, a radius R naught. Obviously, it will intersect this first wavefront at the point O. Okay. Now, he then took a sphere of radius R naught plus lambda over 2. You can see that's going to intersect this sphere at the point Z1, obviously at another point Z1 prime, if you like, that's diametrically opposite, and he took this entire cap region over here on this sphere, okay, which is enclosed by that intersection point. So then his claim was that because this point Z1 is a distance R naught plus lambda over 2, which is, of course, that is a phase difference of pi relative to the electric field from the point O. So between O to Z1, there's a total phase difference of pi. He called this the first zone. We call it now the first Fresnel zone. Similarly, you can then take a sphere of radius R naught plus lambda that will intersect at the point Z2, and everything in this region effectively is out of phase with respect to the first region by lambda over 2. So that's also, so Z2 is now out of phase with respect to Z1 by lambda over 2, which is pi, but therefore it must be in phase with the original field from the point O. Okay, and so on and so forth. You can see it covers up the entire sphere in this way. With like different shells or little strips of this Fresnel zone. So the Z1 or this area is the first Fresnel zone. Z2 represents this region, and so on and so forth. Okay, and of course the electric field from the primary wavefront, we can write that. That's just the standard function, a harmonic spherical wave. So it's E naught divided by rho. And all of this is just summarized over here. Each of these is called the Fresnel zone or half period zone. That's because each of them is out of phase by the pi or half period with respect to the previous one. Okay. Yeah, I already said all this. Now, using this, he was able to derive the electric field from any one zone at the point P. I'm not going to go through the derivation here in class. I've already posted a little because it's a bit of math. Okay. So I posted the derivation, the rigorous mathematical derivation in a little video already on the Canvas site. So I recommend you go there and look at it. So there are certain assumptions. In fact, one of the assumptions, as I said, is that the source, the secondary source that's on the wavefront radiates in phase with the primary wave, meaning whatever wave it puts out is in phase with the primary wave. We'll see in a minute that the actual derivation shows that that can't be true, and we'll okay, so I'm going to skip all of this because this is all covered in the video that I posted. Okay. Okay, this is so far. So as you can see, there's a bit of math, but I go through all this in the text in the video, and we end up with this result over here. Okay. Sorry. This result over here. Okay, so this is just EL, the electric field from the Lth zone is basically dependent on L as just -1 to the L plus 1. So every adjacent zone will have a different sign in front of it. So, right, the first zone, the second zone, etc., will be out of phase with respect to each other by -1. And then the rest of this is just some, okay, this is just a sine wave. Okay, that's normal. And then these are all just some, none of these depend on L. As you can see, EA, rho, lambda, all of this, none of this depends on L, the zone number. But KL, of course, depends on the zone. Okay, KL is the obliquity factor. Okay, because the angle which each zone makes relative to the point P is going to keep increasing. Okay. So that's what I summarize here. E over K has no L dependence except for the sign. So E over K is just a constant times -1 to the L plus 1, which is just dependent on the sign. So and adjacent zones are out of phase, which you already understood intuitively from the construction. And the only other thing to remember is that as L increases, K decreases, because the angle keeps increasing, so that is true. Okay, and I'll come back to this in a minute. So now let's take M zones that are at the point P. Okay, let's take the sum of these M zones. Remember, the total field at the point P is the sum of all of these zones together. So let's take some M zones. E is the sum of all of these M zones. So I'm going to first assume, so you can write this obviously as magnitude of E1 minus magnitude of E2 plus magnitude of E3 plus etc., plus minus EM. So you can see that depending on whether M is odd or even, there will be some contribution or not on the final. But Fresnel's beautiful, this is a really beautiful mathematical trick. He was able to show how the sum can be approximated. Okay, so let's first take the case that M is odd. Okay, so what he did was, suppose M is odd, then he divided up, he kept all the odd contributions as they are, and then the even contributions, he broke them up. Okay, he took all the even contributions as they are. So you can see E2, E4, EM minus 1, which is even, those are kept as they are, and he broke up all the odd contributions. So the odd contribution is even over half over 2 plus even over 2. Then E3 is E3 over 2 plus E3 over 2. So those are all coming in with the plus sign, right, in the sum. Okay. So therefore, he just kept those as they are, and then he grouped these terms together. So you have E1 over 2 minus E2 plus E3 over 2. So you're seeing you have an even zone. Okay, and it's coming in with a negative sign relative to the contribution from its adjacent odd zones, the mean of those relative contributions. Okay, so well, the obliquity factor is a concave function. What do I mean by concave function? It looks like this. Okay, if we plotted 1/2 1 plus cosine theta between 0 to pi, it'll look like this. Exactly, that's actually what I did. Okay, well, you can immediately see for a concave function, the very definition of concave function is that a point over here, for example, this point over here is always going to be greater than the mean of the adjacent points that are on this. That is, it's going to be greater than the average, the chord that joins those 2 points over there. Okay, so EL must always be greater than EL minus 1 plus EL plus 1 divided by 2. Okay, this is the very definition of a mathematical definition of a concave function. Okay. So if that is true, then if I go back to that sum over here, you can see each of these things is basically the center point. This one comes in with a minus sign, but then these two are obviously less than this minus sign by this because of the fact that it's a concave function. And therefore, the total sum must therefore be less than the first one plus the last one. Okay, because all the in-between ones came in with a negative sign. Okay, so this E is lesser than the first plus the last. Because of this fact. Okay, so that is one way in which we have broken up the sum. But if M is odd, we can also break up the sum in a different way. Okay, which is now we keep all the odd contributions as they are, and we break up all the even ones. Okay, so now as you can see, this is E1 minus E2 over 2 minus blah blah blah. So exact same idea, but now we are keeping all the odd contributions as they are and breaking up all the even contributions. Well, as you can see, this is going to have, again, all of these guys are going to come in now with a positive sign, because this is negative and then this is minus of that. So that's all going to come in with a positive sign. And then we are left with just this term and this term. Okay, we can approximate for these purposes that E1 and E2 are roughly the same magnitude. So this term over here is just E1 over 2. So adding these two terms together is just E1 over 2. And then adding these two terms together is just roughly EM over 2. And what I've said now is basically that because all of these terms came in with a negative sign, or because of the minus sign in front of that, these all came in with a positive sign, E is now greater than E1 over 2 plus EM over 2. Well, and of course, I should mention these are, I probably should have written this more carefully. These are lesser than or equal to, or less greater than or equal to. Okay, that's always the case for a concave function. Sorry about that. But anyway, okay. By that argument, then therefore E, because of it can't simultaneously be lesser than or equal to or greater than or equal to, we have that E must be approximately the sum of the first and the last zone divided by 2. Okay. All right. So the first zone divided by 2 plus the last zone divided by 2 is the total field from all the secondary wavelets coming from that primary wavefront. And another way to picturize that is, you have the first, I just drawn the first phasor from the first zone, and then the second zone is exactly opposite, but slightly smaller due to the obliquity factor. Then the next one, etc. And you can see very quickly it's going to converge to a value roughly halfway in between. And we will show that more rigorously in a minute. Okay. Here on the right-hand side, what I've done is instead of just keeping track of A1 plus A2 and just following it along, I've actually kept track of the sum. So the first one is capital A1, which is just A1. The second one is A1 minus A2, and therefore this must be nearly 0 because those almost cancel out. But then the next one adds up again. So you can see this keeps growing, and like that tortoise that's like going by halves every single time as it moves towards a final point. In the end, it will eventually converge if m were to go to infinity. But of course, we don't need to even do that, as we'll show in a minute. So if m is even, by the way, I had chosen the m is equal to odd case, but you can do m equal to even. You'll get an exact same result, except E1 m is now the electric field is now E1 over 2 minus EM over 2. But what is this EM that I keep talking about? If I have the entire unobstructed primary wavefront, M is the very last sort of contribution, the zone, which is coming from the point O prime opposite to the point O. Because, as I keep increasing the radius of my constructing spheres, eventually I'll encompass also the points that are opposite to the original point O on the wavefront. Let me see if I can show you that. Yeah, right here. So as I keep increasing the radius of my spheres that are intersecting the primary wavefront, eventually I'll create a sphere that is so big that it encompasses the point O prime. Okay. Well, the point O prime is diametrically opposite to the point O. So the electric field from this point, a secondary wavefront from this point O prime at the point P, due to the obliquity factor, that angle is exactly 180 degrees. And now, what did I say? That must exactly give rise to a 0 because the obliquity factor is 0 for theta equal to pi. So therefore, this EM over 2 is in fact 0. And therefore, we get that the total electric field, now we have done essentially the sum of all the secondary wavefronts from that primary wavefront using this Fresnel zone construction. And what we have shown is that that entire sum is just equal to the sum from the first Fresnel zone divided by 2. Okay. So this is the beautiful result from Fresnel because, this is obviously, as I've said, this problem is if you want to do it rigorously by verifying the equation and so on, it's a very difficult integral and so on with boundary conditions to solve. But by using this beautiful geometric intuition, he was able to show this result that E is just approximately the contribution from the first Fresnel zone. Okay. And so now we can write that contribution. We know what the first Fresnel zone E1 is because, as I said, I wrote down that function. And that is just this K1. And then all of these guys are just the contribution for the source strength and the distance and so on. So that is already derived. As I said, it's in the video that I posted. So now, of course, this was for the sum of all the secondary wavelets coming from that primary wavefront. But if I had ignored the fact, because there's no obstacle here, I can simply propagate the primary wavefront from the point O to the point P, okay? Which is because, remember, the original problem was there's a source at point O, and we want to calculate the field at point P. Now, if there's no obstacle in between, then the wavefront can also just simply propagate from O to P without any obstruction. So I can actually write down the electric field arriving from O to the point P, not by calculating the sum of all of these secondary wavelets, by just simply assuming that there was no primary wavefront, no secondary wavelengths, just assuming that the wavefront arrives directly from the point O to the point P. And that is just, again, you'll have a 1 over, because it's a spherical wave, you'll have 1 divided by rho plus R naught, which is the distance between O to P, E naught. And then remember, when we first started, we wrote it as cosine of this function, the phase. You can see that this is almost equal to this one, except for 2 things. Okay, the first is, of course, the factor up on top, K1 EA rho lambda, which is E naught. That just fixes the constants such as EA rho lambda must be equal to the source strength over here. Okay, so that's just a constant, not super important, but we see this very important thing that the primary wavefront and the sum of all the secondary wavefronts is out of phase by sine, by pi over d. So if I assume that the secondary wavelets were radiating in phase with the primary wave that arrives at those secondary wavelets, I would get the wrong answer for the actual wave that arrives at the point P. So to fix that, we have to assume that the secondary wavelets actually emit out of phase by 90 degrees. So of course, again, I can give you no rigorous justification, but by doing this sum, Fresnel was able to show that in fact, this must be true if you did the rigorous theory. And it turns out that indeed, when Kirchhoff did the final rigorous solution of the Helmholtz wave equation in free space, he was able to show that in fact, that the electric field arriving, he integrate over any aperture that you want, then indeed has all of these factors. So you have an obliquity factor, which he was able to derive from first principles, but also he showed that there is this extra phase pi over 2 coming in from the rigorous solution. But Fresnel was able to intuit that there must be this phase factor pi over 2 by simply following this this very nice idea of the Fresnel zones. Okay, so I've talked a lot about the Fresnel zones. So now, okay, we'll get to this question towards the end of the class. Maybe we can do it now. Okay, so this is one of your Canvas questions. Okay, so maybe. Okay. So far we have just taken the contribution from each of the Fresnel zones, but there's an interesting geometrical construction which will help us to understand the effect of putting in an aperture of different size now. So we need to understand, suppose I put in an aperture with different radii or diameter or whatever, then how do I predict the total electric field arriving at the point P from this aperture? To do that, we're going to create a vibration curve. We did a similar thing for the Fraunhofer case as well. If you go back and look, we talked about how we can do for a single slit diffraction pattern, we can build up the vibration curve, but there we didn't take into account some of these subtleties like the obliquity curve factor and so on. Okay, so the same idea applies. So we're going to take the aperture, or in this case, we're going to take each Fresnel zone. We're going to divide it into smaller parts, just like we did for a single slit. We took the single slit and we divided it up into small parts, let's say 9 of them, and each of them is like a small little phasor, and then we add up all of these phasors. Well, the same idea here. I'm going to take the first Fresnel zone. Remember, for the first Fresnel zone, the starting phasor, which is from the central point, and the final phasor, the last one, which is the one that comes, which is pi, which is lambda over 2 distance away from the point P, extra lambda over 2, then that phasor in the end must be pi phase shifted relative to the starting phase. So we know the starting and the ending points must be exactly pi phase shifted with respect to each other. So then if you divide up these phasors into smaller subzones, each of them with a radius now lambda over 2n, lambda over n, where n is going to infinity. So basically each subzone phasor will make an angle pi over n with respect to the first phasor. Okay, so this is just like, again, with the Fraunhofer diffraction, except now we take into account the obliquity factor. So each of these phasors is slightly smaller than the previous one. Okay, and that means that instead of just going along a circle like we did in the Fraunhofer case, this will actually spiral in a little bit. But the last phasor will again be pi phase shifted with respect to the first phasor. Okay. All right. So this is just the vibration curve. And so corresponding to each Fresnel zone, the vibration curve swings 1/2 turn. So you can see here, starting at the point OS, it swings a half turn to the point ZS1. ZS1 is just corresponding to the point Z1 over here. Okay, because that's where it's pi out of phase with respect to the point O. Okay, point O over here. Similarly, the next one, ZS2, will be pi out of phase with respect to ZS1, which means it must be back here. So this swings out back again so that the final phasor is pointing opposite to this phasor, the tangent, if you like, to the curve. This tangent and this tangent are directed opposite to each other. Okay. You can think of it mentally as there's a little arrow, which shows, the direction in which we're going around this curve. Okay. And you can see that it doesn't quite come back in the Fraunhofer case, this would have allowed us to say that it's exactly 0 for the destructive interference from the slit, and we would get a 0 or a minima. Here it is a minima, but it's not quite 0 because of the obliquity factor. Okay. Okay, and one thing to note is that the point where this Z2 is lying on this wavefront, it has a radius, right, away from the center. That radius is going to be proportional to M, the zone number, or L, if you want to call the zone number L zone. So, for example, the 100th zone radius is only 10 times the first zone, which means that these theta and k of theta will initially change rapidly because square root of M will kind of like initially change rapidly, but then it's kind of just slowly just grows effectively as M gets larger or L gets larger and larger. So the spiral will start to basically not immediately go to 0, but it'll just tighten. Okay, so the spiral will slowly tighten and eventually will finally approach 0 at the very end of the OS prime. Which OS prime now corresponds to the point O prime, which is directly opposite to O. Okay. Okay. So if I want to find the relative phase between any two phasors, say O, let's say I've taken some, this is the first zone, and here's a point A which lies in the first zone itself. Okay. And I want to find out what is the actual field at the point A, or in this case, what is the total resultant field from this point A. Well, what I do is I take first the phasor from the point O. I locate the point A along this vibration curve, which I'll explain how to do that in a minute. And so this point A has a tangent to this curve, and the angle between them is beta. Okay. And then, so I simply find that angle between the tangents to the vibration curve. That's the relative phase between O and A. And now I just sum up the phasors in between. The resultant is the phasor from O to A. Okay. So that is the total resultant phasor. And beta, of course, is the angle now between A and the point P, for example. Okay. So, so that is basically how you find the points on the vibration curve and how you calculate the resultant phasor from O to A, which will now make an angle delta with respect to the original phasor. Okay, so that brings me to the last little topic here, which is very interesting, I think, because it comes up with a non-intuitive result. So now we're going to do the Fresnel diffraction at a circular aperture. Okay, and that's the nice thing about Fresnel diffraction. Circular apertures are actually easier to handle than the rectangular apertures. Okay. So if M is even, if the number of zones that are enclosed by the radius of this aperture or the diameter of this aperture is even, then we know that the total sum E equals E1 minus E2, E3 minus E4, plus EM minus 1 minus EM. Well, we know that they are going to cancel pairwise. We know that, E1 is almost equal to E2, E3 is almost equal to E4, etc., etc. So E is roughly 0 if there are an even number of Fresnel zones in this aperture. The radius of the aperture is big enough that there are an even number of Fresnel zones. So the first will cancel with the second, third with the fourth, etc. And that if M is even, then they'll cancel almost exactly. But if M is odd, then what happens is, again, we can just pair up all of the terms except the first one, for example. Because the first one, as we said, is the largest one. Due to the obliquity factor, that will be the largest term in the sum. So, and all of these will now cancel out pairwise. And therefore, E must be approximately E1 from the circular aperture. Okay. Well, now this is an interesting result. Why is that? Because remember, I showed you that if I didn't have any aperture, no aperture at all, then the field at the point P is exactly E1 over E2. Well, exactly to a good approximation. Okay. Which is half the field from the first Fresnel zone. And now I've said with the addition of an aperture, I can either make the field 0, okay, it's smaller than the unobstructed wavefront, or I can make it double the unobstructed wavefront. So that's interesting. Whenever I introduce an obstruction into a situation where there is no obstruction, I would expect normally the field would always go down. But now I'm saying that at the point P, there's a possibility the field will actually go much bigger. It will become twice as big as not having any aperture at all, not having any obstacle at all. Okay. So that's the interesting result. Well, of course, the intensity. So as I said, the intensity can be either 0 or 4 times the intensity of an unobstructed wavefront. What this means, of course, is if I'm going to have more intensity at one point for conservation of energy, there must be less intensity at other points. So therefore, you get a fringe pattern. Okay, that's what this is basically saying. Okay, so we get in fact a circular fringe pattern because of the circular symmetry. And so if m is not an integer, we get some value in between 0 and 4 times the unobstructed intensity. And you can calculate, depending on how big the aperture is. So AS is representing the size of the aperture. So I can find where AS is on the vibration curve and simply calculate the field from O to AS, or if it's getting up to, almost the first Fresnel zone or bigger than the first Fresnel zone, then it's going to circle around. So we can use this vibration curve to calculate what the actual field will be and therefore what the intensity will be. And so, so initially, as you can see, if it's roughly half the Fresnel zone, we'll get half OS AS is half, and then it increases to OS ZS1, which is the maximum value, and then reduces to OS ZS2, which is the minimum value, and there are 2 Fresnel zones, for example, and so on and so forth. And finally, when the aperture is very, very large, it's almost like the unobstructed wavefront is coming through. That will just be OS to OS prime, which, as you can see, is half of the distance from OS to ZS1. And again, which is what I was explaining, that you can get 4 times the intensity from the unobstructed wavefront when you have an aperture. Okay. What about, so everything I've said to you so far is I'm sitting at the point P and I'm opening or increasing the size of the aperture. But of course, in most cases, it's easier not to do that, but to simply move off axis from the aperture point, from the center of the aperture, and observe the circular ring pattern, because it's hard to continuously expand and contract an aperture. Well, it's the same idea. What we have to do now is when we draw the Fresnel zones, remember the Fresnel zones were drawn by taking the source point, the image point, okay, and constructing a line between them that intersects with the aperture here. So that is the initial ray or point around which we are observing the interference. As I move off the axis to the side, now I have to just draw these lines that connect back to the original point S, going through the point O1, basically. Now here, or O2 here, or O3 here, and draw again the Fresnel zones around these points. So basically, I would construct a sphere that is intersecting this O3 from this point P3. I would take first the radius R0, which is the distance from here to here, and then I would do R0 plus lambda over 2, R0 plus lambda, etc. And those will give me all different Fresnel zones. But you can kind of see what's happening. It's almost like, instead of moving the point P, it's almost like I was moving the aperture back and forth. It's equivalent to saying that instead of going like this way off the towards the left on the point from the point P, I keep the point P fixed, and I simply move the aperture to the right. Okay, and that's what is sort of depicted here in this graph. So first, initially, let's imagine that the aperture was big enough to enclose 2 Fresnel zones. Then at the point P, we would have a minimum of the intensity. Okay, because the first and the second one cancel. Now I move the Fresnel zone over to the right a little bit, and now you can see the next Fresnel zone starts to creep in. So now the intensity increases a little bit. Now as I go further to O2, now there's an extra little bit of the third Fresnel zone and entering. In fact, a lot more of the third Fresnel zone has entered, and now even a little bit of the fourth one is being seen. And then as we go further, very deep out into the shadow, in fact, then you'll get many, many, many Fresnel zones, and they'll, constructively and destructively interfere, and you'll get essentially circular ring patterns. Okay. All right. So so that's just summarized here. At the point P, 2 zones are visible. So electric field is 0. Point P1, part of the third zone shows, so you get a little more bright fringe. And then at point P2, zone 2 is more hidden, zone 3 is more visible. Since zone 3 and zone 1 here, right, this zone 3 and zone 1 are in phase, right? For Fresnel zone, the first one and the second one are out of phase, then the third one will again be in phase. So then again, we'll get a bright spot here, okay? Okay, so, and then I'll ask you to think, okay, what happens at the point P? Hopefully you'll be clear. Okay, I gotta stop here. So I'll pause. There was a problem I wanted to do. Since I don't have time, I'll post a video again, going through the solution of the, okay.